I'm on the Charles River in the city of Boston. Despite its tranquil appearance, this is actually one of the busiest stretches of water in America. Not above the waves, but below them. There are more underwater tunnels here than at almost anywhere else on the planet. In fact, if you were to connect them end to end, you could start to form an underwater link between the United States and Europe. Today, we're going on an adventure through the history of Boston to discover just how to make that transcontinental link. Completed in 1904, the East Boston Tunnel is the oldest underwater rail link in America. It connects the eponymous East Boston, including a major international airport, to the main city, carrying about 70,000 passengers per day. Counterintuitively, it's much harder to dig through soft soil than it is through solid rock. That's because when you have a firmer material, you can dig the tunnel now and just add the supports in later. Whereas when you're digging under the softer sand, like underneath a river, then the whole thing just collapses in on itself. A telling statistic is that although we've been digging tunnels for more than 4,000 years, it's only been in the last 200 that we've been able to build them underwater. That's all due to an invention known as a tunneling shield. Here's what it looks like in the workshop. A riveted steel semicircle, 10 meters in diameter and about 3 meters thick. With this interior view, you can really appreciate the insane loads it was designed to carry. 2 such shields were constructed and then lowered into massive pre-dug shafts on either side of the river. The actual excavation works in a 3-step repeating process. First, the shield is pushed into the soft soil using some hydraulic jacks. Next, protected by the shield, workers then remove the material, which gets carted up to the surface. A significant portion of that international airport I mentioned earlier is built in the soil extracted from this very tunnel. At this point, if we were to then remove the shield, the roof would cave in. So to stop that from happening, a strong internal wall of concrete and steel is fabricated directly beneath the shield. Once the sides are ready to take the load themselves, the jacks are reactivated and the shield slides onwards into the dark. 30 years later, an almost identical technique was used to build the Sumner Tunnel, but this time to service Boston's growing love of the automobile. What's weird about this tunnel is that while the cross-section that was dug was very clearly a circle, if you look at it today, it's much more rectangular. That is a lot of extra dug material that doesn't really go to any use. So why have they tried to put a square tunnel in a round hole? At the deepest point of the crossing, there are about 250 tons of sand, soil, water and ducts pressing down on every meter section of length. That is a huge amount of force. So to see if withstanding that force has anything to do with the shape that your tunnel is, I've built my own test using some folded up piece of paper and a fish tank. We've got a circular section, the type that was cut in the tunnel, a square, which would be most efficient, and finally a triangle, because I've heard that triangles are the stronger shape. To see how they withstand some load, I'm going to be pouring in a bit of sand and a couple of bricks to see which one breaks first. The triangle crumbles first, followed by the rectangle, and then finally circle is last to fall. Given the extreme deformation that we saw, I wouldn't feel particularly safe under any of our tunnels, least of all because they're made of paper. However, it was very clear that circles worked the best. That's because their smooth sides and lack of corners meant that there were no stress concentration regions, allowing the stress to be evenly dispersed and the structure to last longer. This means that if we're going to be building a transatlantic tunnel, or indeed any tunnel under a high load situation, then circles are the best shape to pick. Our tunnel bore will take us about 400 kilometers off the coast, although as we descend past the continental shelf, even our cylindrical shell will be crushed by extreme pressure. On top of that, you'll eventually run into the mid-Atlantic ridge, which has weekly magnitude 5 earthquakes and actual lava. We need a tunnel that is above the sea floor so that it doesn't get crushed by the pressure, but is still below the surface so it won't get destroyed by hurricanes and pirates. A special sort of tunnel pioneered within this very parking lot. Now, I could proceed to explain how the tunnel works within said parking lot, but I think I found somewhere a lot more interesting just up ahead. Welcome aboard the Beaver. a replica of the 1773 training ship, which was the ground zero for the Boston Tea Party. Late at night, a group of around 100 colonists stormed aboard, intent of dumping its cargo of taxed British tea directly into what is now the Fort Point Channel. About 200 years later, it was ground zero for another revolution. But this time, instead of the American Revolution for Independence, instead it was the Boston Big Dig Revolution for better transportation. As it turns out, the properties that make it such an attractive place to put ships in, namely its central location and massive size, have also made it a nightmare for Boston's road and rail. The Big Dig was a mega project constructed from 1991 to 2007, with the goal of opening up the city and cutting back on traffic. This had actually been attempted before, in the most 1950s American way possible, with a massive elevated roadway right through the CBD. The Big Dig took a different approach, by replacing these motorways and adding in some new ones, but all underground. Most relevant for this episode, the new Ted Williams Tunnel beneath the Charles River needed to be connected to the Massachusetts Turnpike and Highway 1, a route that passes directly through the very large and very central Fort Point Channel. The only problem with this proposal is that space was incredibly tight. On that side, we have the US Postal Service, and on this, the world headquarters for the Gillette Company. And below me is the red line of the subway system, which is the busiest part of the entire network. So we can't go over the river, there's no room, and these companies weren't gonna move. And we can't go under it either, there is a really old train line in the way. The only solution was to go through the Fort Point Channel. Building underwater is incredibly difficult. As you can imagine, if I were trying to assemble this box, then the duct tape wouldn't stick right, the cardboard would disintegrate, and if I were wearing scuba gear, I'd have lots of trouble just trying to fold it up in the first place. I did actually try to rent some scuba gear to demonstrate just how difficult it would be, but it's actually illegal to swim in the Charles due to some relatively unsafe levels of blue-green algae. There are workarounds for each of these situations, like by hiring specialist divers with underwater equipment and with concrete which actually works in this sort of situation. However, these are all incredibly expensive and best left to one-off tasks. Ironically enough, the first step in building underwater should be to get rid of the water. With the Fort Point Channel crossing, engineers took advantage of what's called a casting basin, in what is now the car park which we saw earlier. This is where a temporary dam is constructed facing onto the channel, behind which a pit gets dug. Because we're really good at making things on dry land, this gives us the perfect opportunity to do some optimizing. With a regular tunnel, you can have a maximum of 2 teams working at any time, one on one side of the water body and one on the other, tunneling to meet each other in the middle. However, now that we have a casting basin and all of the above ground manufacturing benefits that entails, we can engage in a little bit of parallelization. You see, if I had to build one massive tea chest all by myself, then it would take some time. But if we split it into 3 smaller sections and have the Sons of Liberty helping me out, then we can do the entire thing much faster. In the same way, rather than taking hundreds of years in order to construct our channel crossing, instead we can do the entire thing in just a few months by converting all available beachfront property into casting basins. Looks like we're all pretty much done. Let's grab some of the actual tea chests and show King George just what we think of him.
These, sir, are the tools that King George and his parliament will use to rob you of your natural British rights. Will you pay this tax on tea?
No!
Then ready! 1, 2, 3! Huzzah! Well done.
Once manufacturing of the actual tunnels was complete, the basin was flooded and sections floated out into position. To stop the red line from being crushed, pylons were installed, extending deep into the bedrock. When the signal was given, the ballast tanks were flooded and tunnel sections sunk to come rest on these supports. Using these techniques, we could build a tunnel all the way through the oceans, kept in place with some massive pylons. Alternatively, rather than filling the ballast tanks completely up, we could carefully control their volume, allowing us to remain neutrally buoyant, a bit like a massive submarine. We could keep it in place with some tether lines or some carefully controlled thrusters. Boston's underwater tunnels have not only shaped the face of the city, but also the lives of all those who live within it. With 100 more years of innovation, who knows what we'll create? This has been James Dingley from the Atomic Frontier. Keep looking up.